All right, I think we're good. So we're going to start by talking about this thing called linearization. But really, if you can find the equation of a tangent line to a curve, you've done a linearization. It's just kind of, it's doing a tangent line, but it looks a little bit differently. But it comes from the idea of local linearity. So if I have some curve, some point that I'm interested in, say it's at A, and I want to know the equation of that line tangent. We've done this before. Okay, so basically, the way that we did that was we made an equation. So it was y equals, the slope of that line is f prime of A x minus A plus f of A. Okay, now that's just written in kind of a different form, but that's how you would go about doing that. Okay. Now, this right here, let me just do something real quick, just to kind of show you where that comes from. Your derivative is a measure of slope, right? Right? Yeah. Right? Okay, good. So a slope would be the change in the y over the change in the x. Or another way of looking at that would be y minus f of A over x minus A. So all I've done is I've taken this and this, which are equal to each other, and I've solved it for y. So I took this x minus A, multiplied it by this, and then added f of A onto the end of it, and then boom, ended up with this. So it's kind of it's a bit of a formula for your tangent line. Okay? So, and you've gone through this process like I said. Okay? Now, the context of this, like I said, is local linearity, which means if I were to take a look at this spot where I'm doing the derivative, and I were like on your calculator, like to zoom in closer and closer and closer and closer and closer to that one little spot on there, the curve itself would start to resemble a line after a while. Okay? And so the theory is, as you zoom in closer and closer, eventually you don't see the curve anymore, but what you really are looking at is this, the tangent line. The curve starts to become the tangent line as you zoom in closer and closer. Does that idea make sense? That this curve, as you get closer and closer, is going to start to flatten out, and then eventually it's going to look like that tangent line that you're actually making through that point. Okay? So that's the context we're working within here. But really, at the end of the day, when you're doing the calculation of it, it's just finding the equation of a line tangent at a point, which we've done before. Okay? So when they ask for, what is the linearization of blah, that's what you're going to do. Okay? And instead of using y, they call it L of x for linearization. But it's just a function notation. Just like f of x is the same as y, L of x is the same as y. It's just a function notation for it. But a linearization at x equals a is going to have the following equation then. L of x is equal to f prime of A times x minus A plus f of A. Okay, so it's the same equation as this. It's just, like I said, they take the y and make it an L of x. Okay, and so the theory is that then, so for values of x close to A, f of x is approximately L of x. Think about that for a second. Look at the graph. Does that make sense? For values of x close to a, f of x is approximately L of x. The value of the function is approximately the value of the tangent at that spot. Okay? So think about this little box that I drew right here. Okay? If my only x values were allowed to be ones that are really close to a, right around it, do you see how the y values of the tangent line and the curve itself are very close together right there? Okay? So we can almost use the tangent line as a way to approximate the actual value of the function. Because sometimes evaluating something on the tangent equation is going to be easier than evaluating something in the actual function itself. In fact, there's going to be some where doing it by hand is impossible to do on the actual curve. But if you can do it on the tangent line itself, then it's actually doable. Okay? Now, if the values of x are not close to a, this is not such a good method anymore, right? Because as we get further away from a, those things, they tend to separate quite a bit, right? Okay? So right over here, like if I let x get really, really large, these two are starting to get further and further apart, and then it doesn't become a good approximation anymore, right? But locally, it's pretty decent, and we can use it. Okay? So that's what we're going to do. We're going to try by getting its linearization first, and then plugging numbers into that to approximate what we actually have. Okay? So, I'll give you an example here. So let's say we've got the function f of x equals the square root of 1 plus x. All right, so we're going to find the linearization at x equals 0 and use it to approximate f of 0.02. Okay, so first question for you, what's the a in this one then? So we're talking about all this linearization at x equals a and all that business up here. So for this problem, what is a? 0. Okay? So I'm going to try and approximate f of 0.02. Is that relatively close to a? Is 0.02 close to 0? Yeah. So this should be a decent approximation then, right? I'm trying to find it very close to where my linearization is happening at. And so I should have a pretty decent approximation when I'm done. Okay? All right, so let's do the linearization. So f prime of x is 1/2 1 plus x to the negative 1/2. Okay. And I'm going to use that to help me because my linearization equation in this case is supposed to be f prime of 0 times x minus 0 plus f of 0. Right? I'm just taking this right here, and now a is 0, so it should look like that. Okay, so let's see if we can fill this out now. What is f prime of 0? One half. Okay. Right, because if I got my derivative here, f prime of 0 is 1/2 times 1 to the negative 1/2. That's a half. So that's 1/2. X minus 0, well, that's just x. And then plus f of 0. So up here then, right? F of 0. What's that? Which is? 1. Yeah. So my linearization equation is 1/2 x plus 1. So I want to approximate f of 0.02. Okay? If I were to try and do 0.02 directly into this thing, do you see how that's kind of a problem? Okay, we can't do the square root of 1.02. I don't know what that is. I can only do square roots of certain numbers, and then I'm stuck. But 0.02, can we plug it into this thing and get an answer? Yep. Yep, this is just a line, right? We can plug numbers into that. So L of 0.02 is 1/2 times 0.02 plus 1. Well, what's 1/2 of 0.02? You guys are kind of slow this morning. What's 1/2 of 0.02? 0.01. Good. So my linearization gives me a value of 1.01. So what that means is that the square root of 1.02 should be really close to 1.01. Okay? So this is our conclusion then, is that f of 0.02 should be somewhere very close to 1.01. Well, okay, we got a calculator. Let's check it out. Are we close? So the square root of 1.02. Yeah, not too bad. Here's what I got. 1.00995. Is that pretty close to 1.01? Yeah, pretty darn. So we did well there. Okay. Let's take it back one step here a little bit. We're going to do the same type of process. Let's approximate the square root of 48 using a linearization. You're going to have some questions where this is all they tell you. So you have to come up with the function. And you have to determine where the linearization should happen at. So you got to come up with f of x, and you got to come up with a. That would be appropriate for this question. Okay? So, for this, you can pretty much just stick with that. F of x equals the square root of x. Now, I want the square root of 48. Is there a square root that is kind of close to that? 49. We know how to do the square root of 49. So our a should be that. It's the number that when you plug it in is the one that you know that's really close to the one you actually want. So 49 should work. Okay. So we're going to do a linearization of square root of x at 49. Okay, so that's going to be our process here. So we're going to do the linearization of f of x equals the square root of x at x equals 49. Okay, so L of x is going to be f prime of 49 times x minus 49 plus f of 49. All right, so derivative. One over 2 square root x. So for my linearization, what is f prime of 49? 1/14. Good. Yep, it'd be 1 over 2 times the square root of 49. So 1/14. X minus 49, well, you can just leave that as x minus 49. That's fine. And then what is f of 49? 7. All right, so there's your linearization equation. And what am I going to plug in for x into my linearization to approximate my square root? Not the square root of 48. Just 48. Yeah, because remember, my function is the square root of x, and I want the square root of 48, so x is 48 when I'm checking this thing. So L of 48 is what I'm looking for. That should be my approximation here then. So it's 1/14 times 48 minus 49 plus 7. All right, well, 48 minus 49, that's negative 1. So it's going to be negative 1/14 plus 7, which gets you, what will it be, 6 and 13/14. So it's 13/14 there, not 18. Sorry, it's kind of small. So written out as a decimal, our approximation here is 6.92857. We'll take it out that far. Okay. So the linearization tells us it should be somewhere in that neighborhood. Okay. So what actually is the square root of 48? At least as far as my calculator is concerned. Calculator is telling me 6.92820. Not too shabby. Pretty close. All right, so that's using that idea of local linearity, that around where you're taking the derivative at, or where you're doing the linearization at, values of the derivative and values of the actual function are very, very close to one another. Okay, or values on that tangent line, rather, not the derivative. Values on the tangent line and on the curve itself are very close to each other. Okay, so that's the linearization. Whoops. We also need to do some Newton's method here. We're probably going to run out of time, but we'll see. All right, Newton's method. So here's the idea of this. This is a completely separate topic, okay? Newton was one of the two guys that was kind of the father of calculus, like we talked about. And he came up with some really pretty creative ways to use derivatives to help things were difficult to do. And one thing was approximating zeros of polynomials. That's not a real big deal. If you have a calculator trying to figure out where the zeros of a polynomial are, you just graph the thing on your calculator and figure out where that's at, just using the function on your calculator to do that. But up until about 20 years ago, people had no other way to do the zeros other than factoring and using the quadratic formulas and all those by hand kind of methods without the calculator at their disposal to help them. And another method that they had at their disposal that they could use was this Newton's method, which kind of paved the way for how your calculator does the zeros. I don't know if you guys ever wondered about that, how the calculator figures that out. But your calculator actually is using Newton's method. It does some little slopes and things to pinpoint where the zeros are at. But in any event, here's the idea. Let's say you've got some curve, okay, some function here, that has a zero right here. Okay? But you don't know where it is. Okay? This is where it actually is, but you don't know where that is. Let's say you make a guess, and you say, I think that the 0 is actually over here. We'll call it x1. Okay? Alright, so then you take that number, you plug it into the function, and you get a value. And, oh darn, it's not 0. I picked a wrong one. But you take that point, make a tangent, doing calculus. You are capable of figuring out where that tangent has 0, because it's just a line, and we can do that by hand every single time. Okay? So, alright. So now I'm here. I figured out where that 0 was right here. Now we're at x2. If I repeat the process, now how I'm closer to the actual 0. If I repeat the process, let's evaluate it at this new place, the original function. It's right here. Oh, darn. It's not actually a 0 again. But if I make another tangent line, repeat the process, now I'm here. Call it x3. Do you see how every single time that I do this, I'm pulling myself closer to where the actual 0 is? Okay? Now, this is one of those situations where you're probably never going to actually get perfectly landed on the 0, but it'll pull you really, really close really, really quickly. Okay? And so you can be accurate up to a certain number of decimal points that you can be confident of after a while. Because if you keep getting the same answer and it's like the same 4 decimal places at the beginning, every time you do it, you can be confident that the first 4 decimal places of that 0 are going to be those first 4 decimals that you got, because it keeps repeating itself. So that's what we're going to do. We're going to approximate zeros using Newton's method, accurate to so many decimal places. Okay? Then we're going to use our calculator to double check and see if we actually got there. Okay? So before we're done today, let's see if we can do it. Okay? So it's basically making a whole bunch of tangent lines and then figuring out where the zeros of those are. And to be able to do this thing effectively by hand, use a little formula here that this is another one of those situations where it stems from the equation of the tangent line. I don't really have time to show you all that. Your book does a nice job of doing that, actually, if you're interested, but I'm guessing probably not. So we're gonna use this. And basically, this x sub n is your it's the nth estimation. And then x sub n plus 1 would be the next estimation. And we're going to use this little formula and repeat it over and over and over again until we get the same number of decimal points at the beginning that we can be confident of, however accurate we want to be with it. Okay? So, let's put this in action for a second here. Okay, so let's use Newton's method to solve that equation then. X sub 3. And you have to come up with where you think the first, or where you think the 0 would be approximately. Now sometimes looking at an equation you have to kind of shot in the dark and see what happens. So what number, if you plug it into this, will give you something that's kind of close to 0? 0, okay. So that's called our seed. So our seed, x sub 1 is equal to 0. We're going to start with that and see what we think. See how this helps us. Okay. So does the name make sense why it's called a seed? Seed is where things begin. That's the beginning part, yeah. So, all right. So our f of x is x to the third plus 3x plus 1. Prime of x is 3x squared plus 3. Okay. So to find the next closest estimation, x sub 2, we're going to go through this little formula here. So x sub 2 is equal to x sub 1 minus f of x sub 1 divided by f prime of x sub 1. And now we got to just plug numbers into this thing. So x sub 2 equals 0 minus 0 divided by f prime of 0. And let's see what that gets us then. So we're going to have 0 minus f of 0 is 1. F prime of 0 is 3. So 0 minus a third, we're at negative 1/3. Okay, so apparently negative 1/3 is a little closer to where the actual 0 is than 0. Okay, so now that becomes our x sub 2. And then we repeat the process. Now we take that negative 1/3, plug it in, all three places again. Okay, so now we're going for x sub 3. So it's going to be negative 1/3 minus f of negative 1/3 over f prime of negative 1/3. And see what that gets us. Now here's where you're probably going to want to just start using your calculator. And what I'm going to have, like on your test, I'm going to have you guys using scientific calculators, so you can't just graph it and cheat. But you can at least plug numbers into functions and such on your calculators. Okay. So let's just finish this step right here, and then we'll be done for today. And then, yeah, plan on coming back tomorrow. So negative 1/3. Oh, we got to plug it into f. Okay. So negative 1/3 to the third plus 3 times negative 1/3 plus 1. So we're getting here negative 1/3 minus negative 0.037, and then f prime of negative 1/3, 3 times negative 1/3 squared plus 3. That is 3.333. All right. We'll come back to that tomorrow. All right. So I'm going to pick up where we left off yesterday, guys. We were in the middle of this problem where we were using Newton's method. Just a quick review here for you. So we got this little formula here that we can plug into. And every guess that we have gets us a little closer to where the 0 actually should be. And so we have to take what our guess is and then minus f of that number divided by f prime of that number. And that gives us the next estimation. And then we repeat the process. And we can do this as many times as we want. Usually the goal is going to be get it accurate to like 3 decimal places, or get it accurate to 5 decimal places, or something like that. So as soon as you have 2 answers that have the same first 3 or 5 or whatever it is decimal places, then you know you've arrived at what you need. Okay. So for this one, we didn't really set a tolerance that way of how precise we wanted to be. So let's say we'll go 3 decimal places on this one and just see if we can do that. So far, we started with the seed of 0, figured that was pretty close to where this would be. And I said if you pick a number and plug it in and get pretty close to 0, that's usually a good seed. So we picked 0 because when you put 0 into this function, you get 1. And 1's pretty close to 0, so that that'll get us a good head start, and then just kind of see where we go. So the next estimation that we had after we plugged in 0 into this formula, we ended up with negative 1/3. So x sub 2 is negative 1/3. Plug that one in, and we're still working that one out right now. So I grab my calculator here, and let's see where we end up. So we got negative 1/3, and then minus negative 0.037 divided by 3.333. And those decimals, too, those are all rounded off as well. So kind of keep that in mind as we go here. But, all right. So then we end up with negative 0.3222. We'll take it out, those four. Well, we should probably go further than that. If we want it accurate to 3, how about we take this one out to 1, 2, 3. We'll take it out 6 places. And we're just looking to see when we can get to a spot where the first 3 decimal places remain the same after we do it. So we're getting close, though. We started at 0, then we were at negative 0.3 repeating, essentially. Now we're at negative 0.322232. So there isn't a lot of difference between these. So we're zeroing in on it pretty quickly here. All right, so x sub 4, our next one then. So we're going to take this, negative 0.32232, and then minus f of that. Divided by the derivative of that. All right, and we're going to see what we get this time. So I'm going to have to come down here because I'm running out of space. 3222232 minus, okay, so f of that should be a very small number. So let's see. So that number to the third plus 3 times that number plus 1. Yeah, pretty tiny. So we get negative 0.0000155 divided by f prime of that. So the derivative, so 3 times negative 0.32232 squared plus 3. And that gets us 3.3115 essentially. And there's a bunch of zeros after that. So, okay. So let's see what that gets us now. So negative 0.32232 minus negative 0.000155 divided by 3.3115. All right, so we're at negative 0.32218. Okay, so I wanted to be accurate to 3 decimal places. I've done it, right? I can know for sure that the first 3 decimal places are going to stay the same because from here it's only going to get more accurate, right? So 0.322, 0.322. I'm still holding on to that 0.322, which means my next one I should still have it, right? As it gets closer and closer and closer to the actual. So if my tolerance was, we need this thing accurate to 3 decimal places, I've got it. My answer would be negative 0.322, would be where the 0 is. Okay, so this process, yeah, it can be a little tedious. Okay, on a test or a quiz, I'll try to keep it, I'll either say, give me what the estimation is after 2 or 3 iterations. An iteration just means that many times through the process, okay? So I might ask it that way, or I'll say something like, make it accurate to 2 or 3 decimal places. Something that's not a lot, so that you're not sitting here doing this forever. And so I'm going to try and keep it to like x sub 4, maybe like at the worst. Okay, no worse than that. So you're not spending a ton of time doing this. But that's the process, though. Okay, involved with doing Newton's method. So I don't want to do another example because it's going to take some time. So, but does the process make sense, though? How we go through and do that? I wasn't leaving anybody in my dust there. Okay. I think the hardest thing with this, and you're going to have this little formula memorized at some point, is just remembering this, what order this goes in. The derivative is the one on the bottom when you do it. So it's the guess minus f of the guess divided by f prime of the guess, f over f prime. If you can remember that, then you're usually in good shape for remembering the formula and using it correctly. So, okay, moving on. We're going to talk a little bit about differentials, and then we're going to be done. And you guys can have some time in class to work. All right, so this section, as you've probably found already, is a little bit of a hodgepodge. It's a catch-all of all these different derivative application things that are kind of like these small ideas. So the whole linearization thing we talked about yesterday, Newton's method, differentials, they're all related to derivatives, but their functions are all kind of different. They're all doing different things. So a differential is something completely different from all this other stuff, too. So I'm going to actually read a little bit out of your textbook on differentials here and kind of use that to get started. So here's what it says. This is on the bottom of page 237. It says, Leibniz used the notation dy dx to represent the derivative of y with respect to x. The notation looks like a quotient of real numbers, but it is really a limit of quotients in which both numerator and denominator go to 0 without actually equaling 0. That makes it tricky to define dy and dx as separate entities. Since we really only need to define dy and dx as formal variables, we define them in terms of each other so that their quotient must be the derivative. Okay, so here's what that's saying. Dy dx. The first thing they said was, it looks like a quotient, right? It looks like a division problem. Okay, and dy and dx are not actual like variables like we're used to seeing them. Those are limits. Okay, we talked a little bit about them when we first defined what a derivative is. It's really at the heart of things. It's a limit. Okay, so they were saying, so it's hard to define dy and dx kind of by themselves because really they're defined in relation to each other. It's the change in y compared to the change in x. Okay, and so dy dx is kind of, they have to go together. You can't take a dy and then say, well, just by itself it's really this. And we kind of have stepped around that a little bit and said dy is kind of, well, it's kind of like the change in y, and dx is kind of, well, the change in x. But really they're kind of this pair that comes together. It's the change in y compared to the change in x. Okay, and so we kind of talked about it this way, where he said, all right, so dy dx is a derivative, so dy over dx is equal to f prime of x. So that's kind of taking Leibniz's notation, dy dx, and Newton's notation, f prime of x, bless you, and sticking it together. So then if you really want to define dy and dx alone, think of this as like a little mini equation that you could solve for one or the other then. Okay? So dy dx, bless you again, let's assume that that is a quotient, okay? And I want to have a formula for just dy, okay? So just think algebra. How would I do that then? How would I solve that equation for dy? Right. So dy equals f prime of x times dx. So a differential is kind of saying, okay, so if you want to have something for dy all by itself, really the only thing that you can say is it's f prime of x times dx. Because of this dy dx and f prime of x, they have to go together. They are the same thing. So, okay, if I'm going to define it as something, it would have to be this. Okay, so that's called a differential. Dy and dx kind of by themselves-ish, but they have to be in this little equation, but are differentials. Okay? So, what can you do with a differential then? Well, you get a question kind of like the following. So you might have something that says, okay, so find... Is it really? Come on. Excuse me one moment. Okay, I'm going to go with that for now. Okay, so we're going to find dy for y equals x to the fifth plus 37x at x equals 1 if dx is 0.01. Okay, and this is just a purely like algebra type problem when you get down to it, okay? So if we use that equation we came up with, dy, the differential dy is equal to f prime of x times dx. For this particular problem then, dy is going to be f prime of 1 because we're doing it at x equals 1, and dx is 0.01. Like that. All right, so this function right here, then I have to do its derivative, right, if I'm going to use this f prime of 1 in here. So y prime is 5x to the fourth plus 37. So if that's my derivative, then f prime of 1 would be 5 times 1 to the fourth plus 37, which is actually 42. Oops, not 5, 4. Okay, so now I have a value that I can plug in here. So dy is equal to 42 times 0.01. So dy 42 times 0.01, 0.42. Okay, so hooray, I got an answer for dy. But what the heck is that really? I mean, what did we just do? Kind of confusing still, right? It's just like, okay, great, we took this thing, we plugged numbers in, and we found dy, and it's 0.42, but what meaning does it have? Well, what you're really doing here is, I don't know what this function looks like specifically, but let's say it's like this curve right here, okay? So what we just did was we said, okay, at x equals 1, so here's 1, there's the point on the graph of f of x. So if we were to put the tangent line on here too, here's our derivative, or at least the slope of this is the derivative. And we did a dx of 0.01. Okay, so this is not going to be to scale at all, but let's say 0.01 is over here. So we moved over 0.01. So now we're at 1.01. Okay, so if we went over that much, and we want to know what is the corresponding delta y that goes with that, then that would be how far up do I need to go to get to the tangent line there. So this is your delta x, and then going up from there to get to the tangent line would be delta y. Okay, so we're saying from this point of tangency, if we scoot over this tiny little bit, how much are we going to have to scoot up going delta y to get back onto that tangent line? Okay, because the dy dx is equal to the derivative, so it's the slope, right? So dy over dx, change in y over change in x, is a slope, and it's the slope of that tangent line. So what we're doing is we're just kind of evaluating to where on the tangent line we'd have to be if we moved over that certain dx. Okay, so that change in x or delta x, what's the associated delta y or dy that goes with that? That's what we did. And so we figured out that if we go over to 1.01, this change that we're going to go up to get onto that tangent line would have to be 0.42. Okay, so that's kind of the the graphical side of things there, of what exactly it is that you're doing to get there. So, all right. So, how can we use differentials in some like story problems, that sort of thing, or real life, however you want to look at it, type stuff. So let's do one of those. Say we've got a circle. And let's say this circle is increasing in size, okay? We're going to use calculus, we're going to use derivatives, differentials, all that kind of stuff. It needs to be changing somehow, right? So the circle is changing in size, and the radius increases from a equals 10 to a equals 10.1, and we'll say that's in meters. So we're going to use dA to estimate the increase in the circle's area. All right, so here's how we can do that. Area of a circle. So it would be area equals pi r squared. All right, so what's the derivative dA dr of that equation? You're close. Don't forget about the pi. Pi is just a constant, right? So if you do the derivative of r squared, it's 2r, but if you do the derivative of pi r squared, it's what? 2 pi r, yeah. Okay, so dA dr is 2 pi r. So if I'm going to use differentials, though, I can change this equation, kind of like we did before. So now I have 2 pi r dr. Okay, r is the value of the radius when it starts to change, and dr is the change in the radius. Okay, and dA is the change in the circle's area. So let's write that stuff down here. So dA, change in area, dr, change in radius, and then r, radius before change. And so this equation right here will help us to estimate the change in the area if I know the change in the radius and the radius's value before things started to change, which I can do because I have all that information up here, right? So I can plug that stuff in. dA is going to be 2 pi. The radius before the change was 10, and the dr is 0.1. All right, so if I multiply that all together, and let's leave the pi in the answer because we're gonna double check this in just a minute. But 2 times 10 times 0.1 is 2. So our dA is 2 pi. What should be my unit for that? 2 pi what? Meters squared. It's a change in area, right? So it should be a measure of the same as you would have for area. All right. So apparently, and this is just an estimation of change, okay? Just so you know. If the radius increases from 10 to 10.1 meters, the area is going to be approximately changing by about 2 pi square meters over that. Okay? Now, we can, in this particular example, because this is kind of a simple equation, we can double check to see what the actual change is, right? And that requires no calculus. I could ask this of my geometry class and they could do it. So what is the, or how do we figure out the actual change in area then? From a radius of 10 to 10.1. Okay, so the original area, pi times 10 squared, is 100 pi. And then the area after the change, 10.1 squared. So what is 10.1 squared? That is 102.01. So what's the change in area there if we got 100 pi and then 102.01 pi? Mm-hmm. Okay, so like I said, this won't always be possible, but for this one we could do it because it's an easy equation. But the actual change in area was 2.01 pi, and our approximate change in area was 2 pi. So pretty darn close, right? 2 pi versus 2.01 pi? Yeah, not too bad. Oh, and this should be meters squared as well. Okay, so that is one way that a differential can be helpful, is that you can estimate the change in something. If you have a given equation you can use, okay, like the area of a circle, then we can compare the change in one variable versus the change in the other. And actually, this is going to be the type of thing that we're going to be doing on Thursday and Friday of this week, is we're going to be talking about related rates, okay? So dA and dr, those are each rates, right? The change in the area versus the change in the radius. And when those are related rates because of this equation, we're going to be actually doing this very type of stuff all through that section with a whole bunch of story problems and that sort of thing. But that's the idea, though, okay? Let's see if I want to do another one or not. Okay, we'll do one more. Make this the last one. All right, so there's this equation. I'm stealing this from your textbook. So V equals K R to the fourth. And that models volume, models the volume of, I believe it's blood flow. Okay. As a function of its radius. Yeah, okay. And this is going to be at a fixed pressure. How will a 10% increase in affect V? That's what we're going to try and figure out. Okay, so first things first, let's take the derivative of this thing. We're going to use that to help us do this. So if I've got V equals K R to the fourth, so dV, bless you, dr, bless you. Remember, k is just a constant. It's just a number. We don't know what it is, but it's just a constant. So what would be then the formula for dv dr? There you go, 4k r to the third. If I'm going to write this using differentials, then dv would be 4k r to the third dr. Okay. So, let's see then. Okay, so then we want to figure out, sorry, just had to double check something. So the relative change in v is going to be this fraction dv over v. Because we're going to check out how is the change related to what you started with. So dv over v. So we're going to figure out what is that ratio then. Okay, and we can plug some things in for that because we have formulas for both dv and v now. Okay, these two. So this relative change then is going to be 4kr to the third dr over v, which is just kr to the fourth. And that thing can be simplified quite a bit. There's k's that'll cancel, there's some r's that'll cancel. So we end up with 4 dr over r. Okay, so here's what we can pull from this then. So dv dr, I'm sorry, not dv dr, dv over v, that's what we just calculated, is equal to 4 dr over r. Okay, and so we've got this relative change in v, and then here's your relative change in r, the change in r versus how much r we had. Okay, so if we've got a 10% increase in v, I'm sorry, 10% increase in r, right? So if we got a 10% increase in r, then what's going to be our relative increase in v then? If this ratio is equal to 4 times this ratio, and this ratio we said had to be 10%. Don't overthink it. This is 10% times 4. 40%. Thank you. Like I said, don't overthink it. So a 10% change in r will be a 40% change in v because of that equation. It's 4 times as much based on what we got there. Okay, so that's kind of a different way that differentials will get used, is we can make a comparison without actually like plugging numbers in and doing all of that. This type of a look at differentials, I'll be honest, you're going to do a lot less of. It's going to be mostly that other type that we did, that last example where you have some numbers where you can plug in and do some comparisons and stuff like that. So, okay, call it good. Course sites should have everything that you guys need, but I'll double check it. So, have the rest of the class period today to work, and then tomorrow will be online as well.